that seem impossible to solve head-on? Well, in chemistry, some reactions are exactly like that. They're too slow, too messy, or maybe even too dangerous to actually run in a lab. So how do chemists figure out how much energy they release? It turns out they use a really clever backdoor, kind of like a secret weapon that we're about to check out.
And it usually starts right here, in a classroom, with a chemistry problem that makes you feel totally stumped, right? You're asked to find the energy for one reaction, but you're only given the data for a bunch of other, seemingly random ones. It might look like you've hit a dead end, but it's actually a trail of breadcrumbs leading you right to the answer.
So this really gets to the core of the problem. Some chemical reactions are just incredibly difficult to measure directly. I mean, just imagine trying to perfectly create methanol from some graphite, hydrogen, and oxygen all in one clean step. In a real lab? Well, it's pretty much impossible.
So that leads us to the big question, right? If you can't actually run the experiment, how in the world do you find the answer? Is it just a guess? Nope, not at all. Chemistry has this super elegant solution. You just take an indirect route.
Okay, this is where chemists get really smart. They use this powerful idea that acts like a secret backdoor to find the solution. It's not about doing the impossible reaction, it's about using what you can measure to figure out what you can't.
And that tool, it's called Hess's Law. At its heart, it's a beautifully simple idea. It basically says that nature doesn't care about the journey, it only cares about the destination. The total energy change from your starting chemicals to your final products is always the same, no matter how many different steps you take to get there.
Let's break that down with a quick analogy. Imagine you want to know the change in height from the ground floor, we'll call that point A, to the top floor, point C, of a building. The main elevator's broken, so you can't go directly. But you can take the stairs from the ground to the 5th floor, that's point B, and then maybe a different elevator from the 5th floor to the top, point C. All you have to do is add those two changes together, and you get the total change in height. Simple, right? Hess's law applies that exact same logic to chemical energy.
Okay, theory is cool and all, but let's see how this actually works with a real-world example. We're going to put on our chemist hats for a minute and solve for the energy it takes to form methanol, a reaction that, you guessed it, we can't measure directly.
So, our objective is super clear. We need to find the standard enthalpy of formation. Now that's just a fancy chemistry term for the heat change that happens when 1 mole of a compound is formed from its basic elements. It's a really crucial number because it tells us how stable that compound is.
This equation right here, this is our destination. This is our target. We need to figure out the energy change when graphite, hydrogen gas, and oxygen gas combine to make exactly 1 mole of liquid methanol. This is our point A to point C.
Now, since we can't measure that reaction directly, we're given 3 clues. These are related reactions that have been measured in a lab. Our job is to treat them like puzzle pieces and put them together to build our target equation.
And here is our evidence. We've got the combustion of methanol, the formation of carbon dioxide, and the formation of water. And you can see each one has a known energy change or delta H value. Okay, now the fun begins.
All right, we've got our clues, but we can't just add them up the way they are. We have to manipulate them, flip them around, multiply them, until they perfectly match the pieces of our target puzzle.
So here's the game plan. First, looking at our target, we need 1 mole of graphite as a reactant. Equation 2 gives us that perfectly, so we're going to leave that one alone. Second, our target needs 2 moles of hydrogen gas, but equation 3 only gives us 1. So, simple enough, we'll multiply that whole equation by 2. And finally, we need methanol as a product, but in equation 1, it's a reactant. So what do? We reverse the entire equation.
And here's the most important rule of the whole game. Whatever you do to the equation, you have to do the exact same thing to its energy value. If you multiply the equation by 2, you multiply its energy by 2. And when you reverse an equation, like we just did, you have to flip the sign of the energy. It makes sense, right? If a reaction releases 726 kilojoules going forward, then going backward has to cost you 726 kilojoules.
So, here's what our puzzle pieces look like now. We have our reversed equation with its new positive delta H. We have our original graphite equation. And we have our doubled hydrogen equation with its doubled delta H. See, all the pieces are now in the right place.
Now for the really satisfying part, the final assembly. We add up everything on the left side of the arrows and everything on the right side. And just like in algebra, we get to cancel out anything that shows up on both sides. So, the carbon dioxide, gone. The 2 waters, gone. Even some of the oxygen cancels out.
And what we're left with is exactly the equation we were aiming for all along.
The puzzle pieces fit perfectly. We've built our target equation. Now the last thing to do is just add up the energy values that go with our manipulated equations to find our final answer.
And there it is. We just add up our new energy values. We have a positive 726 plus a negative 393 plus a negative 572, giving us a grand total of negative 239 kilojoules per mole. That's our answer, and we found it without ever having to step foot in a lab to run that impossible reaction.
So, we can now state with total confidence that the standard enthalpy of formation of methanol is negative 239 kilojoules per mole. We solved the puzzle. But what does that number, and especially that little negative sign, actually tell us?
Okay, we've got our number. But what's the story it's telling us? What is the real significance of that negative sign? This is where the chemistry gets really cool.
Here's the key takeaway. A negative sign means that energy is released when that compound is formed. You can think of it like a ball rolling downhill. It releases energy and it ends up in a more stable, lower energy state at the bottom. So that negative number tells us that methanol is energetically more stable than the individual elements it's made from, the carbon, hydrogen, and oxygen.
And that brings us right back to where we started. We've just walked through all the logic and all the steps to solve one of chemistry's unmeasurable puzzles using Hess's law. So now that you've seen exactly how it's done for methanol, what about that original problem from the classroom? Can you take these same steps and apply them to find the answer for methane?